Hey everyone, class is no longer over. Let's do some chapter regression. Whew. Busy day, busy day. Let's do some reviewing and some learning. Samuel, good to see you here. What do you want to cover? We could do we didn't do regression during class. What do you want to cover? Yo, Ty, Louie, good to see you there. What do you want to cover? I took a quick break. Woo! At least one question. Let's do another at least one. You ready? Let's do an at least one problem. You'll say the things you want to do. We'll do them in the chat here. Let's do them. Okay, so 643, chapter 10, or 12. 12, at least one problem. The hard questions, then we'll do some regression. At least one problem. Okay, so the number one way to do these at least one problems is to draw it out. So we're going to do a problem right here. And let's say the following. Okay, you have 3 questions left. All right, 2 questions left. 2 questions left on this 201 exam. You've studied really hard, and you just need to get one more question to get an A. Turns out you're good at guessing. The questions have a 70% probability of getting them right. What is the probability you get at least one right? Okay, does everyone see this? So we need to draw, this is the steps I like to do an at least one problem. So if you see one of these problems, you got to draw it out. So what letters am I going to write first? Who's seen me do a lot of these and you know what I'm going to start to write? If you don't know how to do this, follow along. The more you do this, the more you practice it, you can solve these. You follow the steps, you solve it. You know how to solve it at least one. So what are we going to do? We're going to A and the probability of A. Great job. So right there we have A, which is the outcome. So A is just an occurrence of something. And then probability of A is the probability of said thing. So we're either going to get the question right or we're going to get the question wrong. And so the probability of right is 70% and the probability of wrong is 30%. Now I make a second table. So we've already got our first, and what's the deal? As Jerry Seinfeld once said, what's the deal with probability tables? What's the deal with the probability table or the sample space of everything that could occur? Now we're reviewing the term sample space. The sample space is everything that can occur, and the probability of a sample space is equal to what? RotoWave bomb points in the chat. It's equal to 1. Shout outs RotoWave. Right? Thank you, RotoWave. So big test tonight, RotoWave. Sample space is right or wrong. You either get the question right or wrong, and the probability of it is equal to 1 when you add it up. It's everything that can occur. So now we're taking a test, and we have left at the end of the test 2 questions. So we want to see the probability of getting at least one correct. So now we're doing another table of what could happen. A is the outcomes, and probability of outcomes are listed below. Just sort of flipping the table, making it easier. Yeah, I like doing it this way. I don't know, for some reason I just like putting it that way. So here we are. What could happen with the questions? What's possible? So there's only 2 questions left. What could happen? Just talk me through it. You got 2 questions left. What could happen? What are the possibilities? What's the sample space look like? So what's the possibilities of things that could occur? And this is the sample space. So the sample space is the things, and their associated probabilities are down there. So what can happen? What could happen here? Boom, Megan's got it right there. And Megan's listed everything that could occur. You could get 0 right, 1 right, or 2 right. Does that make sense? So you could get them all correct. You could get them all wrong. You could get 1 correct. And what we are specifically looking at here is you get at least 1 right. So what we're interested in is this. What are we not interested in? What are we not interested in? We're not interested in what? How would you describe the thing we're not interested in? We know this equals up to 1 right here. If you add them up, it equals up to 1. So what are we not interested in? The probability of what? Getting everything wrong, right? We're not interested in getting none correct. So would it make sense to say you either get them all wrong or you get at least 1 right? So you're either going to get all wrong or at least 1 right. So the drawing shows you to get them all wrong or at least 1 right. One of those 2 things must occur. And they both can't happen, so we can actually use the addition rule right here Because these two things are what of each other? What word am I looking for on the screen? Because you either get all the questions wrong or at least one right. So what word am I looking for? These two things are what of each other? What word? They're mutually exclusive. Exactly. They're disjoint. And they're actually complements. Complements are mutually exclusive because they can't occur because it's this or this. They're complements. They're mutually exclusive. And you can see the formulas for complements up here. So know your formula sheet. So now when you think about this, if you call this x and you call this y, x plus y equals to 1 because they're complements, because this is everything that could occur. So x plus y equals 1. I want to make this clear. We're not putting 2 equals 1 or something. So now we just need to put it into equation. Well, how can we solve for y? Y equals 1 minus x. Then what is x? X is the probability of getting everything wrong. So what's the probability of all wrong? The probability of all wrong, which is x, is going to be 0.3 to the second power. Nice job, Megan. And so you just plug in that x is going to be 0.3 to the second power, and that's the probability of getting everything wrong. So it's everything but getting all the questions wrong. Who feels better on this? If you do these, has anyone done these steps? I've seen a lot of people take notes. Shouts to those people taking amazing notes. When you can draw it out and just write out the question, and you're like, okay, I know what that means, I know what that means, I know what that means. You just have a way of doing it. You can solve them really quick usually because you can just draw out the question. Now, why is it? Well, so what would that be? So 0.7. What is the math of 0.7 to the second power? That would be you get the first right and you get the second right. So then this, what you're finding right here, let's actually write this out a little bit. What you found doing that mathematics is you found 0.7 to the second power, which is 0.49. And then over here, you could solve this one, which is 0.3 to the second power. Who knows the probability you get exactly one correct? What is if this question said, what's the probability you get exactly one correct? What would that be? What's the probability of getting exactly one correct? Well, think we did a different way. It's exactly one correct, which is a totally different question. Exactly one correct. We could try. We'll do one more here. Exactly one. Well, look at the table because this is we're talking about what I have highlighted right there. What do you know about this table? The table has to add to 1, right? So the probability of exactly one correct is going to be and I believe it's 0.42. It is. You're right. Because this has to equal to 1. And what it is you could be right or wrong right or right wrong. And you'd add those. And this would be right times right. And this would be wrong times wrong. But there's 2 ways right here. So this is 0.7 times 0.3 plus 0.7, or well, we could do 0.3 times 0.7. But you can also solve it, and that's what the math up there is showing. Does that make sense? This is right, wrong plus wrong, right. And so you can do right, wrong plus wrong, right. And there's the math of it right there because you're just multiplying these and then just adding them. So this is right, wrong. It's too big of a pen right now. Right, wrong. So right, wrong. And then this is wrong, right here. And then you're just adding them because you could do it one of 2 ways. But it can also be found by just doing the complement. Does everyone who follows what I'm saying right here, like this 42% for getting exactly one correct? And then you know what you could do here too? Use this table now, which I'm going to highlight in light blue. Use this table to find out the probability of getting at least one correct. Use this table. 1 is the probability of everything all together. 1 means if you add them all up, you get 1. Like if you add all these up right here, you get 1. If you add these up, you get 1. Like you'll either get 0 right, 1 right, or 2 right. You either get 0, 1, 1, or 2 right. No, the one in the middle. That was just me also saying they all add up to 1 down here. Sorry about that. That's also just saying it adds to 1. Mm-hmm. Sorry, I wrote it below also. Like that the whole thing, if you think about it, like that's why I put those like bar underneath it. It's like this all adds to 1. Well, how could you do, using what's written for you now, how could you figure out at least one? Using what's written for you now, how could you, look at what I have circled, how could you figure out the probability of at least one? No worries, no worries. The space in the middle, this right here, that means you get one right exactly. That means you get one question correct. You could get wrong right or right wrong. So what you could do is you could just add these up. Or you could do what we did previously and subtract from one this. And does that make sense? Are you seeing it? That you could just subtract like we did here out of one, or you could just add these up because this is one or more correct right there. Because this is you get one correct or you get both correct, like right, right, or wrong, right, right, wrong. We could do one more. I hope I didn't confuse anybody. Let me know your thoughts. Like, keep asking questions. Version 1. Let's do a version 2 of this. And people are saying they want the other side of it. Okay. So, your friend is amazing at fishing. Each hour, they usually catch a fish, with that happening 80% of the time. What is the probability over the next 3 hours let's say 2 hours they fish. 2 hours they fish. One of those hours they don't catch a fish. Okay. So now we got fishing. So what will happen for your friend catching fishes here? They're either what are the two things that could happen during an hour of catching fish? What can happen when your friend is catching fish? The event A and the probability of event A. And let me put the note in the sheet. What are the two things that could occur? They either what or what in a given hour? They either what or what? They either catch a fish or they don't catch a fish. Great job, Ty, right there. They either catch a fish or don't catch a fish. So they either catch or no catch a fish. And the catch is 80% and the no catch is 20%. And then we want to look at what's the probability they don't catch a fish. In one of those hours, they don't catch a fish. Wait, at least, what's the probability in the next 2 hours? One of those hours, they don't catch a fish. At least one of those hours. We'll do at least one of those hours, they don't catch a fish. I want to make sure that's clear. It's at least one. Okay. So now we go right here. And we're going to write A and probability of A. And we have they could catch. What does this mean? So where should I put which line should I do? Should I do line 1 or line 2? And we're saying this is how many hours they catch it. So do we want line 1 or line 2? Where are we going to divide this? Because we want at least one of these hours they do not catch a fish. At least one of these hours, they do not catch a fish. Which line should I do? We actually want line 2. And here's why. Because either this, what is this going to be right here? This is the one we're not interested in. So what is this? What does this represent? Can you tell me conceptually, what does this mean? It's the event. It's going to have an associated probability. It's the one we're not interested in. We are interested in this over here. That means every hour they caught a fish. They caught a fish every hour, right? Does that make sense? So, and so this is like in a given hour they catch a fish. Like it means, oh, I caught a fish this hour, and then the next hour they caught a fish also. They fished for 2 hours. And in those 2 hours, each of those hours, they caught a fish. At least, I know I'm saying at least one, but it means they caught something in that hour. So like each hour they caught something. They had a good hour. They caught something. So at least one of those hours they don't catch a fish is what we're interested in. So they're either going to catch a fish within each of the hours, or what does this mean over here? What happened to them when they went fishing here for these 2 hours? Who can explain why I'm putting a sad face on this? Yay face for the fishes. But what would this mean right there? What does that one mean? They didn't catch in any of the hours. So in none of the hours did they catch a fish. And this would mean either in the first hour they caught a fish or in the second hour they caught a fish, but they didn't catch a fish in both of the hours. Does it make sense? Like they didn't catch a fish in the first and second hour. They only caught a fish in the first hour and not the second, or they caught a fish in the second hour and not the first. So that's what the 1 represents right there. In one of the hours, not the both of the hours, they caught a fish. Follow me? So on the right of the line, it happens. Well, this is the thing we're not interested in. That's why I've shaded this in a red color, because we are not interested in them catching a fish in both hours. We're interested in at least one of the hours they didn't catch a fish, because that's what the question asks. So this is going to be the thing we're not interested in. So I'm going to call that X, and we're going to solve for Y. Now, because this is the full table equals to 1, which means we can rewrite this as 1 minus X equals Y. We're just literally, because this is X plus Y equals 1, because we have everything listed, and the plus would be between it. Technically, it'd be right there. I don't want to make things under the 1 or the 2, because Y is the possibility of 1 or 0 or 1. Does that make sense? So you could, at least 1 hour they don't catch a fish is 0 hours catching a fish, or 1 of the hours catching a fish. We're not interested in the case where both hours they catch a fish. And so what is X equal to? Well, X is they catch a fish every hour. So X is catch and catch. So what is the probability they catch a fish in the first hour and they catch a fish in the second hour? So what is the probability of that? What is the probability they catch a fish in the first hour and they catch a fish in the second hour? What's the probability of that? Which is X. Yep. It's just going to be 0.64 to the second power. Oh, wait. 0.8 to the second power, which is 0.64. 0.8 to the second power, which is 0.64. So that's going to be 1 minus 0.64 equals 0.36. And what you can do is now, since you know this is 0.36, actually, this is 0.64, and this other side of it, the whole thing, is 0.36. The answer to the problem would be 0.36, correct. And since we know this is 0.36, well, 0 is going to have a probability of 0.04, because 0 would be 0.2 to the second power, so that equals that. So what's the probability in one of the hours they catch a fish? You have to deduce it from the problem, Samuel. That's a good question. How do you know if your win or lose decimal is what fills in the X? Because this was catch and catch, because it was the probability they catch in both the hours. The probability they catch in both the hours is catch and catch, because 2 means they caught a fish both hours. So it would be they catch a fish both hours, which is catch and catch. And Zariah, you've said it, this is 0.32. So the probability they catch a fish in one of the hours, not both, is 32% of the time. The probability they catch a fish in both of the hours is 64. The probability they don't catch a fish in any of the hours is 0% of the time. So you can actually fill in the full table, and then you could figure out, just by adding these, that the probability of 0 and 1 is this right here. So you could add those right here to get that associated probability. And the whole thing has to add up to 1. Do people feel a little bit better? Yeah, the middle number is they caught a fish either in the first or the second hour, but not the first. Like, you wouldn't catch it in the first or the second together. This is they catch a fish in both the hours, the second and the first and the second hour they catch a fish. So you have to catch and catch. And then this over here means the first and the second hour they did not catch a fish in either hour. So I'll highlight this in green, but this is what it represents, is in the first and the second hour they did not catch a fish. This one would be they caught a fish in the first, they didn't in the second, or they caught a fish in the second but not in the first. And this would be they caught a fish in both hours, catch and catch. I think there can be the possibility of one question, but you just fill out the table. That's why I'm kind of doing this tricky part. It's a little bit of a tricky one. It can be deduced. We don't do it for bigger questions than if there's only 2 things. Hint, hint, hint. But if you fill out the full table, you can get any question that does this. Like, I'm literally giving like the level 10 questions slightly away. Like, there's a tough question I'm thinking of when I do this. So that is like the hardest probability question we can come up with. There's not like, if you don't know it or can't get it really well, it's only like 2 points of the task. But it's a really like a tough question. It's not tough, you know how to solve it. So it just takes practice. Takes practice in knowing how to write the table and write the set of all things that could occur. Okay, context acting up again. What did we say we're going to do next? So the answer of the problem is that the probabilities. Well, the first question. So what is the probability of at least one of these hours they don't catch a fish? Who knows the answer to the question up above, which is highlighted in yellow? Looking at the table down below, what is the answer to the question highlighted in yellow? The probability in at least one of these hours they don't catch a fish. Exactly. It's going to be this right here. Great job. Yes, Ty, you got it. Nice work. It's this right here when you add them up, because it would be either in 0 or 1 hours they don't catch a fish. Like there was no hour which they caught a fish, or they only caught a fish within one of the 2 hours they caught a fish. The catching a fish thing, I kind of like the example. I might use it again. So I think, what do people say they want to do next? Why is my contact acting up today? Watch it rip. That'd be funny. Maybe haha funny. Oh my gosh. What do people want to do now? Oh, who lives in a pineapple under the sea? Ugh. Regression. Let's do some regression. Hey, Bailey. Yep. Oh, who lives in a pineapple under the sea? SpongeBob SquarePants. Lord and goddess, Horus is he. Chapter 7 and Chapter 8. Let's do Chapters 7 and 8. Let's do the conditions first, because they're fun. Regression conditions. Are there any questions using the applet? Nope. Oh, well, I mean, if you would, it would have pictures, and I don't think they're too bad. We always give pictures, so drawing it out can really help. Going regression versus residuals, yeah, all that. Are bias simply going to be one of the answers? There can be like response bias, non-response bias, convenience bias, undercoverage bias. All those types of biases are right there. Okay, I can see again. Yay, going over regression versus residuals. Okay, so let's do the conditions first, then we'll hop into some of the formulas and stuff, because I think conditions are nice and easy to start with. Then we'll do that next, Bailey. So here we go. We might another time for another one, as in, could more than one be right? Shouldn't be. There'll be multiple choice for those a lot of times. We don't have a lot of written, because then people write under. The answers get weird with written answers. Okay, so here are what are the regression conditions? Who knows and can say for me right now all regression conditions, all 4 of them? What are the 4 regression conditions? What is the 4 conditions? Well, you're thinking of, and that is Chapter 13 and beyond. QQ, straight enough. No outliers. Plot doesn't thicken. QQ, straight enough. No outliers. Plot doesn't thicken. So QQ, straight enough. Great job. 2 quantitative variables. No worries. Okay, let's think about, why is it important to have 2 quantitative variables? Because if you have 2 quantitative variables, you can make a what? Or a what, but more importantly, a what? If you have 2 quantitative variables, you can make a what? If you have 2 quantitative variables, you can make a what? What is graphically made? A scatter plot. A scatter plot is made with 2 quantitative variables. Be very careful. A lot of people call it a dot plot. It's not a dot plot. A dot plot is a lot like a histogram, where it has the dots that stack up, and then you can put a histogram over it. So a dot plot is univariate. You see over there, dot plot is not a dot plot. I know it's got dots, but a scatter plot looks like this. A scatter plot this is a scatter, and this is a dot plot. A dot plot is univariate. A scatter plot is bivariate. So this is one variable, like height, and this would be bivariate, 2 variables, like height, weight. So be very careful. So 2 quantitative variables is easily satisfied by just, is it a scatter plot? Is it height, weight? Is it bake time and yumminess of cookies? So that is what we need for 2 quantitative variables. Simple to check. Just see if you have 2 quantitative variables, and it should make a scatter plot. If there is time on the x-axis, it is a time plot. So that's what 2 quantitative variables means, and that's how we check it. Now, straight enough. Straight enough. Now, it's not the perfectly straight regression condition, because when you do straight enough, is this straight enough? Is that straight enough? What do you think 9 out of 10 statisticians would say? What do you think 9 out of 10 statisticians would say? Yeah. Yeah. It would say yes. And I do want to highlight something because I want to show something here. Give me a second. I like to show a little bit of the advance. It is a little weird, and that's a good answer right there. I think is Zariah right there. Zariah is pointing out that it gets a little bit odd at the end. We'll show the graphic here in a second again. We're loading up our studio. But it got a little bit odd at the end. And here we'll show that graphic. So it got a little bit weird. We would say that, well, the line doesn't, yes, it should go through the middle, perfect. And so this is for this condition, there's the bad part. And then the line is mostly going through the center of it. And we do have ways of checking this. So I can actually check this mathematically. So if I make a linear model right here, a linear model predicting MPG from the weight of a car, from the data, empty cars, and then we visualize the model. Usually you just look at it. So is this straight enough, yes or no? Now, if you notice, it's got a little bit of a bend. You see how this is perfect. At the end, the line is not going through the center. If the line was really good, it'd be going through the center of this. But that's where there's a problem over here. Here's pretty good. A little bit of a problem because all the points are below. You want the points to be cut by the line down the middle. Does everyone understand what I mean when I say straight enough that the points are cut? Like, in the middle right here, this is the amazing part of the model. The model is doing really good right here because it's cutting through the center of these points. Over here on this side, it's not doing good because the line should be theoretically there because that's about where the center of the points are. Does that make sense? And that's not where we're at. I don't think it's that complicated of a condition, but this one does have some issues. Over here, there's a little bit of an issue because the mean of the model is about here. So that's a little bit of a problem. And over here, it's all right. It's pretty decent. So you notice the line, if we were to trace through this, has a little bit of an issue where it's kind of going like this-ish. So it's got a little bit of a bend. We can actually check this mathematically, and I can tell you if it actually passes because I can check my regression. And the answer is it actually fails it. It actually does fail it. This is because the p-value is statistically significant. That is not on your test. P-values are used to check conditions. So that one was iffy, and visually it's kind of like, I don't know. But this one, I would say, for the most part, passes. We'll make it very clear on the test. If the line is bad, it'll be pretty darn obvious. Ones that we usually give on the test to show that things are not straight enough are usually going to be models that are more like something like this, where it's pretty darn obvious fitting a line. Now, can we fit a line to this, yes or no? Can we fit a line to this, yes or no? Can you fit a line to this, yes or no? Can you fit a line to that, yes or no? Can you? Yeah, you can just add a line to scatter plot. Should you? The answer is no, because it doesn't really follow a linear relationship. So straight enough means, does the data generally good enough, or straight enough, good enough, follow a line? So adding a line would be a good idea to model the data, to show what it looks like. So no outliers is what it says. Are there no big outliers pulling the model in a direction? Now, what's interesting is I want you to look at this data and tell me, is there a big outlier? Is there a big outlier, yes or no? Is there a big outlier? Yeah. And it might not look far away from the model because you're like, well, wait, it's on the model. But without this outlier, the model would have probably looked something more like this because the data has no relationship. If you take away the outlier, then all of a sudden the data looks like this. But you can see here it is with the outlier. Here it is with the outlier removed. So the model drastically changes and goes towards the outlier. So here is the data, and then if you add in an outlier, the model's going to go towards it. So it's kind of neat. I love going back and forth in the equations. So with this right here, that outlier is drastically impacting the model, and you can usually see it. They're usually far away. Like a more classic version of an outlier, I wanted to do something a little bit odd. A classic version of an outlier would give you would be something like, and then you put a point down there, and that's going to be an outlier for the model. So what's going to happen is this is the data originally, and then because of the outlier, the model's going to go more like something like that. It's going to pull it down towards the outlier. Would be exactly. There are some models will change when you remove outliers. Outliers have drastic impacts on models, and they pull the model in the direction of the outlier. Wherever the outlier is at, it'll tilt the model for or against it. So if you were to take the outlier here and put it all the way over here, then the original model is going to look like this. And think of it like a teeter-totter. It's going to go through the data, but then this is going to take and pull the model that way. Does that make sense? Because it's gonna tilt towards the model. The point is going to try to minimize its error, the error being the residual, and the model tilting towards it is minimizing that distance because we try to minimize residuals, which that's the residual. And you can see from the new line, the residual is smaller, which is wrecking the residuals for the other one. Does that make sense right there, Zariah? Like outliers will try to minimize their own residuals, but since they're so far away from the model, they'll create this pull that is kind of an undue pull, which we call influence, other terms we use. But it's a very influential point. So there we go. We do not want outliers. Outliers can do anything to regression. They can make it strong, they can make it weak, they can make it positive, they can make it negative, all those things. Now, what graphic do we look at? We want the predictive power of the model to stay about the same. We look at a residual plot to check this condition. So the plot doesn't thicken is if you take your plot Does this one have plot thickening? Yes or no? Does this model? Oh, it definitely does. Yep. So to make a residual plot, you simply take your plot right here of your regression and you make it flat. Let me do this. Really? Where'd it go? Okay, we're going to do like that. Oh, look at this. Now I got like 5 versions to work with. What are you going to do now? Oh, too bad. I can move it wherever I want now. Haha. Perfect. Okay. So there is the residual plot. And to turn it into a residual plot, I just re-express the axes. There you go. So now you can clearly see there is plot thickening and the model's predicted power is getting water. The model's predicted power, and this is a residual plot. Best way to check this condition. The model's predicted power is getting stronger or weaker. Because it's getting more spread out, it's getting more variance weaker. Exactly. There's more variance around the model. The model is getting weaker as the model goes. So it's getting weaker. As you progress to higher values of X, the model gets weaker. So you wouldn't, and you don't want it to get stronger either. You want it to stay about the same. So other examples of plot thickening would be a model that does this. This model is getting stronger, and you don't want to see that either. A model getting stronger shows heteroscedasticity differing plot strength. Which one of these is a good residual plot? Which one of these, A or B, is a good residual plot? Which one of these, A or B, is a good residual plot? Which one of these, A or B, is a good residual plot? B, 100% B. A good residual plot, if you just Google good residual plot, A good residual plot should show no patterns. It'll be random. So a good residual plot, as long as you get ones that are good, like that's not a good residual plot. That's a horrible residual plot. Good residual plots are going to look random. Like that's a pretty good one right there. See, they've been showing you right here, unbiased, homoscedastic, meaning same strength. So that's a bad residual plot. It's funny, you Google good residual plot and you get some bad ones. So you have to, this is a pretty decent one down below. These are bad residual plots because you can see the bend. You can also see the bend in the original model too. That is time series right there. Woo! Oh, it's OTEX. Yeah, this is FPP3, I think. Yeah, look down there. You can see the FPP2, the original Forecasting Principles and Practices. So this is a very amazing book right here, FPP3 and FPP2. If you ever want to learn time series, we don't get much into it, but this gentleman right here is an astounding statistician, and it's his package right here that allows you to do time series. And the book is completely free, so you can learn how to do time series analysis for completely free. Love it. Thank you for him for making the book. That's a great residual plot. Residuals are independent. You see, they're going to be like, yes, good residual plot. That one has some outlier issues and maybe a little bit of plot thickening. Yeah, there's outlier, 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 and these are, oh my gosh, what is that? Is bad residuals, bad residuals. Okay, so we want to see good, and you see they're even pointing out the outlier over there. Look at that outlier over there, and this is some generated data. It's ridiculous. That's a nonlinear model right there. Something going on nonlinear in the model. But you want to see a random pattern. Okay, let's do some concepts. I'm going to stop kicking things under my desk. I'm kicking wires. We don't want to do that. Okay, let's do, what if it's closer but still flat horizontal? Which thing do you mean, Zariah? Does it become a better residual plot as the points become closer together? The model is stronger when the points are closer together. So the model is stronger back here at the bottom of it. So the model's stronger. You don't want the strength to change, though. B is closer. B is a very good residual plot because it doesn't show any patterns. The points are completely random. Yeah. Mm-hmm. So this one is a little bit stronger, but it's also a nonlinear model. This one has a nonlinear because that's the line. This would have came from a model that looked like if you put, well, that's what the true form is. So it would have looked something like this because this is that line right there, which is not going through the center of the data. You can see the bend to the data. And this one over here would have came from a model that looked something like this, and the points are randomly. Does this make sense right here? If you take and make this into a residual plot, do you see how the points are randomly scattered around it? So if you turn this into a residual plot, what will you get? You see, we take this line right here, and you make it flat, and then you re-express it. And you can see it looks like a random scatter now. So now, there it is. And that's what we want to see. We want to see that, but that came from a model that looked like this. Because remember, the residual plot is just examining all the residuals. So there is the regression model. So that's the regression. This is the residual plot of it. Residual sets that to 0. And it tells us how far above things are, above or below the line. So you can tell the positive and the negative residuals, as you can tell right here. So you could see, like, imagine this is where 30 is at. This is 20. This is 10. So what is the residual for this point highlighted in green? We'll pretend that that point is this point over here. What is that residual for that point right there? What is the residual for that point? Who knows what its residual is? So we're asking, what is the residual for that point? Which would be the answer over here. So what is its residual? How far above the line is it? How far above the line is the residual? Or is it how far above the line is the point? Well, it's positive for certain. It's positive, and I've added some numbers there. Well, it's at 30. The point is at 30, but the prediction is 20. So remember, residual, E, which is what we're looking for. So we're looking for E equals actual minus predicted. Now, the predicted is going to be the line itself. The line gives the predicted value. So the prediction comes from the line, and then the actual is this. It is 10. Yep. As best I could draw, it's 10. because, and remember, this is the line, and all it does is make the line flat, the prediction line, because anything on the line would have a residual of what? Like, if we talk about this point right here, that point right there that I'm adding to the model, that point has a residual of what and why? What is the residual of this point right there? It has a residual of what, and why does it have that? Its residual is 0 because it's on the model. So you can see it has a residual of E equals 0 because anything on the line would have a residual of 0 because it doesn't miss. Meanwhile, we could put an outlier in here of something like, here we'll add more numbers, 40, 50, 60, 70, and we just add these tick marks here. And then we go ahead and add in a point. Let's add in a orange point over here. And we're going to add in the orange point right about here-ish. So that orange point would now be on this graphic over here. What is the residual for that orange point? What is, just guesstimate it for me. Guesstimate the residual for the orange point. So the orange point probably has a residual of what? The orange point probably has a residual of about what? The orange point probably has a residual of what? What is its residual? You can see it's actual. It's actual. So its actual value is 20. It's about 20. Well, so its actual value is about 20. It didn't do it perfectly, but I was looking to make it about 20 for the actual value. And then you have to find its predicted value. So its predicted value is the prediction equals 40. Maybe I might have, well, I tried to, it might be a little bit bigger than that. So maybe it's about 44. Does that make sense? Or 42. So 42, if you go up, oh, maybe, Megan, you might be more right than me. Oh, Megan, I think you're right. Yeah, we gotta give Megan some points on this. Okay, wait, Megan's more correct than I am. We're just doing it visually to find the prediction. So, we got to recorrect this. So its predicted value is equal to 50. So since its predicted value is 50 as best, we're just doing it visually here. That means its residual, I have to move it over here now. Its residual is like negative 30. Does that make sense? Its residual, who follows this? Its residual is about negative 30, meaning it's 30 below the model. So you can see it over here on this graphic on the left. This is the same graphic on the left that I have on the right here, where you can see that point with the residual of 0, and you can see the point with the residual of negative 30. But here we put 10 minutes ago that we started doing, or 5 minutes ago we started doing regression, residual plots. Chapter 7/8. Do people feel like they understand this better? The residual equation is residual equals actual minus predicted. This point has a prediction of 50 because of the model highlighted in pink right there. The point is actually 20 because if you go over here to the x-axis or the y-axis, it's 20. And we could even, I'll do one right now where we solve an equation just doing residuals. If I were to tell you predicted height, actually I can get a real equation because when I come up with it, it might be weird. Okay, so data, survey 10. Let's go SciPen for options. SciPen equals 4. And I'm just changing options digits equals 2. Okay. And there we go. Now we'll go here and do M save into LM, height predicted from weight. And this is a good review of regression right here. When we build a regression model, and this is good right here, we won't solve for B1 and B0 by hand. You won't use those equations, but we'll check this out. What do you need to know? Oh my gosh, summary, I couldn't think of the command. What do you need to know when you look at this output? So we've seen this a lot. I was trying to make it so these decimals would change. Is it round? No, that's not going to do it. Yeah. Dang it. What do you need to know from down here? When building a regression model has a what and a what. When building a regression model has a what and a what, which Megan's kind of pointed to it. We have y hat, that's way too big. We have y hat equals b0 plus b1x, right? So when you think about this, the model itself is going to have the following. It's going to have a y-intercept. The y-intercept is going to be b0, i.e. when x is equal to 0, we expect y to equal b0. And then the slope of the model is going to be the rise over the run. The rise over the run is going to be this right here, which is going to dictate the increase we see, or decrease if it's negative. So who can write the regression equation right now? So go ahead and write it for me. Remember, and you can do it to 2 decimals. Just write the regression equation to 2 decimals. Write the regression equation to 2 decimals using the output on the screen. So you have to look where it says estimate of intercept, estimate of the x variables coefficient. So what would be the regression equation using this format right here? So what is the regression equation? Well, we have to identify the components. Great job right there. And make sure to put in Zariah really close, and don't worry, you don't have to write things out on the test, but make sure to throw in the variable names and you've got it. Great answer. So if you look at what Zariah has done right there, we have, that's the wrong one. Here is the slope coefficient because it's related to the x. Notice how the variable right there is related to the x. And then the intercept is right here, and literally it says intercept right there. So we just plug in these values. We say that the predicted height, that's why we put the hat on it, predicted height is equal to 56.34 plus 0.07 times weight. So 0.07 times weight right there. And so this is going to be the intercept, because that's the B0. And this is going to be the coefficient of the slope. And this is the name of the x variable. The name of the x variable is just the name of the x variable. That's all it is. That's all it is. And then the y variable is the name of the y. We'll do a little circle on it right there. It's predicted height. Predicted height is equal to. So now imagine this. Brian is 200 pounds. I gained some weight. Brian is 200 pounds. I just told you x, as in weight of Brian equals 200 pounds. Brian is actually, so Brian's height is actually 75 inches tall. What is Brian's residual? A residual is how much the model misses by. So who can figure out my residual? It's a 2-step process right now to figure out my residual. So can you do it? If you want to figure out your residual too, you're welcome to. But what is my residual? Well, remember, residual, which is E, equals actual, which is Y, minus predicted. And you do get these formulas. So residual equals actual value, whatever Brian's actual height is, minus his predicted height. So if you notice, we know my actual height. So my actual height, which is the Y variable, Y value we're looking at, is this. But we don't know right now my predicted height. To get the predicted height, we'd have to do this over here, because this is what predicted height is. That is predicted height. And when you look at what a residual is, it's how far am I above or below the model. So if you have a point, if I am above the model, my residual would be positive from below. So who knows what my residual is? We have to take and plug in. Something does seem wrong. Well, so you plug my weight in here. You plug in 200. So if you plug 200 into here, what will you get? Solving this equation with 200 plugged in is going to get you what now? Solving the equation with 200 plugged into it, I'm currently solving for Brian's what? Think about if we solve for 200, with 200 plugged in right here, we go 200 times 0.7, 0.07, 200 times 0.07 is that, plus 56.34. Well, might be an error. What does this solve for right here? You might have done 0.7. It'd be 0.07. That might be the issue. Yeah, I think you did yeah, there's a 0. Oh, Zariah, it's my fault because I'm bad at writing things. I did write 0.7. It should be 0.07. So that's my fault. Sorry about that. Totally made a mistake. My fault. Let me throw you some big points right there. It is my fault. I wrote it down wrong. And now we have, and I'm glad you noticed. We'll throw you some big points during office hours right here. So you notice this is Brian's predicted height. So Brian is predicted, height predicted for Brian is predicted to be 70.34. So now you merely just plug in these values to my residual of 4.6 4.66 is equal to 75 minus 70.34 because its residual equals my actual height minus my predicted height. Does that make sense? And there you go. That's got it. So I am 4.66 inches taller than predicted. Does that make sense? I am 4.66 inches taller than the model predicted me. So that's what a positive residual would indicate. I am taller than predicted. Negative residual would mean you're shorter than predicted. So yeah, nice job tying, everyone. So that's just a good example right there showing how to write the model. Now, is this model statistically significant? Why or why not? And actually, we'll screenshot it. So it's, yep, the model underestimated me. You can see the model right there is underestimating me. Good answer. Is this model statistically significant? And when is a model statistically significant? Is this model statistically significant? And when is it? So the answer is somewhere on the screen for is this model statistically significant? And when is it? Is the model statistically significant? Now, when you hear statistical significance, you should think what values? Exactly, when p-value is less than 0.05 and the p-value of the slope. So the p-value of the slope deals, and great job, Jesse, right there. The p-value of the slope deals with the x variable. The x variable, good to see you, Ella. And it is statistically significant because the p-value of the slope is less than 0.05. The intercept is not important here. It's the p-value of the slope. Now, we should also know the r squared. The r squared is about 36%. So it's blank percent of the variation in y is explained by the variation in x. So with r squared right here, it would mean 36% or 36.1% of the variation in height, which is the y variable I wanted to predict, is explained by the variation in weight. So this is the y variable of interest. This is the x variable. So you times this by 100, and you say 36.1% of the variation in y is explained by the variation in x. PROS, basically P. Oh, this says probability of a value greater than the T. So the T is basically a z-score. More on that later coming into class. But p-values are probabilities. So the PR stands for probability of observing something greater than... And actually, you know what would be interesting? Let me see if I can do this. Let me try this. Is GPA capitalized? It is. Darn it. Let's show you something right here. Let me change the digits in the round too, though, because that's going to drive me crazy. Oh my gosh, we're not doing SciPen. We're doing... That's good enough. Okay. Give me 2 more tries at this. Text per day. Trying to get something, Zariah, that you'll be like, no way. Closer. There is one that works perfectly, and I can't think about it. I can't find it. Okay, I'll work with this one. I'll show you why. Pretend for a moment that this t value said -3. It's very close to that. Because here's the thing. If you were to have a z-score of -3 and +3, what percent of area would be between it? If you were to have a z-score of -3 and +3, what would be the area between here? A z-score of -3 and +3, what would be the area between here? So if you had a z-score, we're pretending this is a z-score right now. If you had a z-score of -3 and +3, what would be the area between there? What would be the area between there? Well, the like, you remember the 68 rule? Not 68 for this one, but what would be the amount of area between here? Like how much of the graph is covered? 99.7, right? So 99.7% of area is in between. What does that leave remaining on the outside? What does that leave remaining on the outside? What does that leave remaining on the outside? This is your t equals to -3, and this is a t absolute value, like absolute value of t is equal to 3. So it's one just as extreme. And so that's actually how these are being calculated. So the p-value is the same idea that we've been doing. It's just getting you the area on the outside to find out a value just as extreme. And I was trying to find one near an empirical rule number, because here we go. I wish I could find another one really quickly that's an empirical rule number. That's not one. I want to find one more that's such a good. Let me do this. Attach survey 10 and percent. No. See, that's in about 0.03 again. I want to find a better one. That's not right. Wheat. It's finding extreme stuff. No. Dang it. I want to find a perfect one. Yeah. I'll do a few more. Of course, that one's like highly correlated. Percent funnier than. Can't find a perfect one. 2 more tries. Nope. Last try. No. I mean, you can kind of see it. I was trying to find such a good one that. Wow, that one's really, really correlated. Okay, wait. So you see this one right here? It's kind of close. Because if this t-score had been 1, what would the p-value about be? So if this was basically -1, then what would the p-value be? So if it was at -1 and we went to 1 and -1 and went to the outside, the area over here is supposed to be the area on the outside of the absolute value of the t-score. You see it says absolute value, so that's why we're doing both sides of it, because it says absolute value. So you have to do both sides of it. So what would this be about equal to? And of course, it's a little less than this because it's further out. Like the real answer of this is further out because it's at -1.1 or so and +1.1. So it'd be 30. And you see how this is less than 32 right here because we're further out. I think, Sarai, because it's the area on the outside. So if we were to find an empirical rule number, it's going to be very close to those numbers. There's a little bit more to the t that we'll learn, but the t is basically the normal, but William Gossett corrected it while working at Guinness Beer for smaller sample sizes, so it has a correction in it. Like we talk about these corrections we do, it's a corrected distribution for smaller sample sizes. So, well, I think I take a short break today, I think. Do I? I don't even know what's going on today. Google Calendar. Whew. Yeah, we've done it. Might take a short break, but how are people feeling? Are people feeling a little bit better? And this model does horribly. About 0.2% of the variation in whatever we're predicting is explained by the variation. About 0.2%. It's not statistically significant. It's by random chance what we're seeing. The variation in your percent attractiveness explained by your GPA. But pretty good review of regression. We did a bunch of at least one problems. And I will say this, if you're watching this, watch the review videos and work through the problems. That's going to be some of my best advice. Have people been utilizing the channel? I feel like I worry because I feel like less and less. I feel like with ChatGPT and everything, I feel like more and more I worry. Let me look at the analytics. Usually we have like 2,000 to 3,000 views over the last. I think they changed the page and everything too. Okay, we're getting a lot of views. Okay, I'll take it. Yesterday, a couple hundred views an hour. Okay. Exam 2 reviewed a lot. It's funny, when I look at the most viewed videos, people, you can tell they start the speed runs. The most viewed video is for speed runs is, you see, Exam 2 is getting reviewed a lot. And then people start the playlists, and then they don't. Good job. See, 170 views, and then 88 views on the next one. So I think it's very common for people like, I'm going to watch all of it. Brian said, woo. Did I wear you out? Oh, no. I said woo because I'm decently happy with the views. Back in the day, we had in 2 days over 10,000 views in 48 hours. It used to be before the test. We have a lot more resources too right now, but this is how many views we've had in the last 48 hours. 3,000, nearly 3,000. You can see that spike. That's when class started. But people are watching the videos, and that's what I want, because I think the videos really can help people out. But I can see like what videos are being utilized, what are not being utilized. And I know the exam 2 review game gets used. And that's why I kind of did it like on Monday, because I'm like, well, I think people will watch it Monday and then view it Monday, because I've done it on Friday and then it just didn't work for my schedule. But then people don't watch it on the weekend. Kind of a bummer. I won't be able to study. If you look at, this is the weekend, so that'd be Sunday, and this is yesterday. And there's such good time to study on Sunday. But people usually study the day before the test. Like, if you look at the amount of studying and reviewing, and I'm the same way too. I'll admit it. I do it. With that, we're going to take a break. We'll be back for some in-person office hours, then class, then test. But until then, bye for now, everyone. Good luck. And email if you have questions. I need to check my emails, and then I'll go on a walk. Bye for now.